Right, so now we're looking at March 19, paper 52. First question, we are looking at the reaction between hydrogen peroxide and iodide. So this is a redox reaction. Actually, your iodide is being oxidized into iodine. The rate of this reaction can be found by measuring the time taken for a given amount of iodine. Just to remind you, rate is defined as change in concentration over time. So the concentration here is the amount of iodine is the same. Well, not really the same, but proportional. Okay, the higher the amount of iodine, the higher the concentration over time taken. Okay, if we want to study the rate of this reaction, what we can do is that we can use thiosulfate to measure how much iodine is present, okay, by reacting it with the iodine produced from the first reaction. What will happen is that later on you will see that hydrogen peroxide, iodide acid, which is the sulfuric acid, I believe, and and thiosulfate will be mixed all together. So what happens in that reaction mixture? This tree will produce iodine. The moment iodine is produced, the thiosulfate will immediately, the moment it touches, immediately reduce the iodine into iodide. Okay, so you wouldn't expect to have any iodine until there's no more thiosulfate anymore, which means the iodine is in excess. When there is an excess amount of iodine, then only the indicator will show, okay, there is iodine now, iodine in excess, right? So it says that after the thiosulfate have all reacted with the iodine in reaction 2, any further excess unreacted iodine formed in reaction 1 can be detected using an indicator. So they don't tell us what the indicator is, but I assume that when the indicator changes color, that means iodine is present. Okay? So just remember, indicator shows the leftover iodine that doesn't react with the thiosulfate. Okay, so then they carried out this reaction. A is iodide, B is thiosulfate, C is hydrogen peroxide, and then there's also water for the H plus of this reaction. Okay? The student prepared solution A. So if we go back to the question, solution A is 0.1 mole per dm cube of potassium iodide. Determine the mass in grams of potassium iodide needed to prepare 250 centimeter cube of solution. So what you do is find first the number of moles required for that particular concentration. So you use number of moles is equals to C times V. Once you found the number of moles, since you want to find mass, the relationship is number of moles equals to mass over mR. So you take the number of moles times by the mR of potassium iodide. So mR of potassium iodide is 39.1, just add 126.9, okay? So after working this out, you should be able to get the mass required to make that potassium iodide concentration is 4.15 grams. Did you manage to get that answer? Okay. If you didn't, perhaps you want to copy down my working, but this is basic mole calculation. Okay. Next, the student. So what the question is saying, the student weighed the empty weighing boat. So I have made up some number here. Okay, just so that it's easy for us to visualize. Okay, so the student weighed the empty weighing boat, and then the student add the solid potassium iodide, so that you add the calculated mass. From the previous question, the calculated mass is 4.15. Okay, so we assume that after we weigh the empty boat, just the boat, it's 200 grams. And then boat plus potassium iodide, you get 204.15. Okay, and then if you want to find the mass of potassium iodide added is 4.15 grams, right? However, for this procedure, the student, after he measures the mass of both plus potassium iodide to 04.15, what he did was he transferred the solid to the reaction mixture. Okay? Now, the problem with this is after you transferred the whole thing, it looks like the weighing boat is empty, right? But actually, some solid residue may stick or may be stuck onto the weighing boat, okay? Even like crucible, like if we use our naked eye, we don't see any solid, okay? But we don't know that some of the solid may stick onto the crucible and not all of them is being transferred, all right? So the question is saying this is not accurate. To say that the student has transferred 4.15 grams of mass is not accurate and it's not confirmed. So now the question is asking, how can the student confirm that the mass of solid transferred, which is the potassium iodide, was exactly 4.15 grams? Okay, so there's a modification that can be made. What this person can do to confirm and say, yes, I did transfer 4.15, is to reweigh the empty boat plus residue, just to confirm that the mass is still just 200 grams. If the mass of that boat is 201 grams, for example, that means there's 1 gram of solid residue left that has not been transferred. Okay? So how the student could check the mass of potassium iodide transferred was exactly 4.15. First, the student can reweigh the empty weighing boat plus residue. This is after transferring all the solid. Okay? And then the difference between boat plus Ki and boat plus residue must be 4.15 grams. Then, for sure, he can say, yes, I am confident that I transferred 4.15. Okay, hold on. Okay. Next, the student dissolved the potassium iodide in the 100 centimeter cube beaker in distilled water and transferred the solution form into the 250 centimeter cube volumetric flask. Distilled water was added to the volumetric flask until the volume of the solution was exactly 250 centimeter cube. Care was taken to avoid parallax error. So that means the question is saying that error due to parallax or error due to reading the level of the volumetric flask is not a factor here. Okay, so that's why they say that last statement. Okay, now if you remember, you did this before where you would dissolve solid in a beaker using distilled water and then you transfer the solution, now it's a solution, using filter funnel into the volumetric flask. Okay? Describe how the student should transfer all the potassium iodide solution from the beaker into the 250 centimeter cube volumetric flask. So now, how can we ensure that we do not waste or throw any potassium iodide solution during this making up of potassium iodide solution? What do I always tell you to do? After you transfer, what must you do? You rinse or you wash, okay? So you want to wash whatever that you use beaker, you use stirring rod, you use funnel, you wash it, but don't throw it into the sink, but you throw it into the volumetric flask. This ensures that we have tried to transfer all possible potassium iodide. If anything, if there's any sticking onto the beaker or sticking onto the stirring rod or the filter, the funnel. Another one, okay, so that's right, we want to rinse it. I'll write down the answer later. The next one is how the student should fill the volumetric flask exactly up to 250 centimeter cube mark. Okay, so this question to me is very vague, like how to fill in. I mean, don't you just, add water and make sure that it goes to the level is aligned with the mark on the volumetric flask. But what the answer is looking for is actually, what do you do near the line? How should you add water when you are at the narrowest part of the volumetric flask? How do you add the distilled water? Huh? Sorry? I can't hear you, sorry. Huh? Drop in. A dropper. Okay, dropper, yeah. Yes, you will use the dropper. So the technique is you want to add the water drop by drop. Okay? So basically, I always tell you, add in the water slowly when you're at the narrowest part of the volumetric flask. Okay, so you would want to add the distilled water drop by drop. To answer that, I will answer the first question first. Wash or rinse the beaker and transfer into the volumetric flask. And secondly, Danish said use a dropper to add water drop by drop near the mark. Okay, so you don't want to add in water using the beaker, otherwise you will miss the line or the mark. Good? Okay. Next, I remember mentioning this to you at the start of your practical, but I don't know if you know the reason why. I always say, if you want to use the burette or the pipette, you wash it with water first, yeah, tap water or distilled water, and then you wash it or rinse it using the solution that you are going to use. Do you remember this step? Okay. Do you know why I asked you to do that? Or if you don't remember me saying that to you, do you know why you have to wash the apparatus before with the solution that you are going to use? Yes. So you do not want to change the concentration of the solution that you're doing. But how can that change the concentration of the solution? Okay, so imagine if you wash the burette using tap water, okay? And then it's not dry. So you have some water inside the burette. If you put in the solution, the volume now changes, the concentration of that solution will also change. It will become diluted. As you would expect, it's the same thing like adding water to the solution, the concentration will change, or we say that it will be diluted. Okay? So you do not want your solution to sort of mix with water. That's why you wash it with water first and then you wash it with the solution, you throw it away. So it removes any water in the apparatus from the first step where you wash the apparatus using water. Okay? So explain why this improves the accuracy of the results, because then the solution in the burette is at the expected concentration in bracket. You can say no water to affect the concentration. Okay, so that's something that we tell you to do it every time, but I don't think I've ever mentioned as to why that step is necessary. Okay, next question. The student was given a solution of 0.4 mole per dm cube. Determine the volume that should be added to 100 centimeter cube of volumetric flask to prepare 100 centimeter cube of solution B. Okay, this is something that I believe you have done in biology. It's called dilution. You are given a solution that has a high concentration, 0.4 mole per dm cube. Now they want you to prepare the concentration as in solution B. If you go back to the first page, solution B has a concentration of 0.05. So can you see that what you're required to do here is to dilute the concentration from 0.4 to 0.5, okay? And the volume that they want you to prepare the solution is 100 centimeter cube. Okay. In bio, did you have to learn a formula when it comes to dilution? Yeah. Good, correct. It is the same formula that we're going to use. C1V1, C2V2. For those of you who have not used this formula before, C1 means the initial concentration. This is the concentration of the solution that you are provided with. V1 is the volume. How much of that solution do you need to add? Okay. C2 means the final concentration, the concentration of the solution that you want to dilute it into. In this case, we want it to go down to 0.05. V2 is the total or the final amount of that solution that you want to make. So C1, V1, C2, V2, you should get an answer of 12.50 centimeter cube. Okay, so I've given you all the information. All you have to do is to just work it out. Okay. You okay? Can you work out that number? Actually, for this kind of calculation, you don't have to change the centimeter cube to the m cube because both sides, you will divide both sides, so it doesn't matter. But to make it a habit, I just want you to convert the centimeter cube to the m cube, because if we want to use the concentration, we need to make sure that the volumes are at the same units. Okay? Okay, we will move on to the next part. So this experiment, so what they do is they add 0.2 mole per dm cube of sulfuric acid and then distilled water. So they mix A, B, indicator, and C together. Okay, and then the contents, the stop clock was started, and then the stop clock will be stopped when the iodine form caused the indicator to change color. Okay, so why would the iodine be formed? Let me just explain to you again for those of you who were not here just now. What happens during this reaction is hydrogen will react with iodide to form iodine. Okay, the moment that iodine is being formed, thiosulfate will react with it. So at the start or at the first few minutes or seconds of the reaction, you will not see any iodine being formed because any iodine form will quickly be wiped out or reacted with the thiosulfate. So when will we see indicator changing color? Once all the thiosulfate is being used up to react with the iodine here, then you will have what we call excess iodine or unreacted iodine. So this excess unreacted iodine is the one will cause indicator to change color. Okay? So that means when the indicator changes color, that means there's no more thiosulfate to react with this iodine. Okay? So that's what it means. You then get a table. The table is given. I've labeled my ABCs because I can never remember them. You notice that the indicator, the volume of the indicator, the volume of thiosulfate, the volume of the acid are all the same. Okay, so we are changing only the volume of A, which is the iodide. And if you remember earlier on just now, it mentions we are measuring, monitoring the rate against the amounts of iodine. So you would expect only iodine is being changed. If you change a few things here, then you wouldn't be monitoring the change in iodine. Okay? In experiment 3, trial 2, the indicator changed color as soon as the student added the solution together. Okay? No results were recorded. So that means if the indicator changed color, the iodine is present because that's what I said, right, just now. Indicator will change color the moment it detects the presence of iodine in the mixture. So this means the iodine was not reacted. This iodine did not react with the thiosulfate. The question is asking which step did the student did not carry out. Which step involves adding thiosulfate? Thiosulfate is B. Step 4. You all agree? Yeah? So that means this student must have forgotten to add thiosulfate because if he did, then you shouldn't get iodine produced instantly or immediately. Iodine will only be detected after the thiosulfate has finished reacting with it. So suggest which step the student did not carry out. It would be the step 4, where thiosulfate is being added. Okay, so we can add here S2O3 minus not added. Therefore, it didn't react with iodine. Showing color change of indicator. That answer in bracket is not required for the mark scheme, but that's just a further explanation as to why we have chosen step 4. Suggest why the results shown in the table could be considered reliable. You can see the time taken for trial 1 and trial 2. What it means by trial 1 and trial 2 is just repeat repeat of the experiment. Okay, first time doing it, and then you repeat it the second time. You can see that for each experiment, the numbers are quite close to each other. So we say that the experiment is consistent. Okay, hence it is reliable. So one possible explanation for reliability is when, after repeating the practical or experiment, you still get the same values, more or less the same. Okay. Next, percentage error. Percentage error is also popping up every now and then. What was the percentage error in the Burette reading? So there's a few things before you calculate the percentage error. You need to identify the smallest reading in the Burette. What's the smallest reading that you can read in using a Burette apparatus? Do you remember? So kalau you read the volume on a Burette, macam mana? 25.00, 25.10, 25.20, 25.30. So what's the smallest division here? 0.1. So you go from, it's not easy to visualize because you don't have the apparatus with you. So the smallest reading would be 0.10. Okay? That means the error per reading is half of the smallest reading or smallest division. Okay? That's what we mean. The smallest division is you just take the difference between the two values that you can read of the Burette. Okay? So that brings us to the next one. 0.10 is the smallest reading. The error per reading is half of the smallest reading. But this time, they want you to find the percentage error for the volume of solution A in experiment 5. So if you go to experiment 5, solution used here is 20. When you use a Burette, how many readings do you usually take? Burette. 2 times, initial volume and final volume, okay? So that means, yes, you use 2 readings. That's why you multiply it by 2, initial and final volume. Times by the error per reading over the value used. In this case, we use 20 centimeter cube of solution A in experiment 5. So you should get a percentage error of 0.5%. 0.500% if you want to leave your answer to 3 significant figures. Are we all okay so far? Suggest why a measuring cylinder was used to measure the volume of H2SO4 rather than a more accurate piece of apparatus. Now, the fact that we don't use an accurate apparatus for sulfuric acid means, well, it's probably not that important, okay? What I mean by not important is that the value, whether it's 25.0 or 25.1 centimeter cube of sulfuric acid, does not matter. Whereas for the other solutions, it does matter. 0.10 centimeter cube of difference does matter. Okay? This implies, or this indicates that sulfuric acid is not a limiting reagent. Limiting reagent means once that solution is out, the reaction will stop. In this case, it doesn't matter whether the volume of the sulfuric acid is accurate, more or less by a few centimeter cube, it doesn't matter because it's not a limiting reagent. What is the opposite of a limiting reagent? Excess. So the reason for this is because sulfuric acid is in excess. Good, thank you. Okay, it's not easy to get to that answer, especially if you're in the exam, you're under a lot of pressure, and you really don't know what the question is asking for. Okay, so in this case, sulfuric acid is in excess. That's why if you use more, you use less, it doesn't really matter. So you don't have to be accurate. Just use a simple measuring cylinder and you'll still be fine. It will not affect your reactions or calculations. Okay, for experiments 1 to 6, state the independent variable. The independent variable is usually seen as your x-axis, what you can change, what you will plot on the x-axis. Going back to the first part of this experiment, we are monitoring the rate for a given amount. Okay, so the rate, sorry. We are going to monitor the change in amount over the change in time, which is the rate of the reaction. Okay, so what we are changing, if you can see here, we're changing solution A. Yeah, you change the volume of solution A, you are also changing the concentration. Everything else stays the same. So that's not a variable. That is the control. It stays constant. Okay. So what changes here is the volume of solution A, but more accurately is the concentration. Okay. And since we're studying or investigating rate, change in concentration over change in time is what we are investigating here. Concentration of iodide ion. Okay, next, you have to complete the table. Basically, log V, you just take the log to the base 10 of your volume V. T average time taken is you just add the time for trial 1 plus the time for trial 2, divide by 2. I hope everyone managed to do that, okay? So for each experiment, you add trial 1, trial 2 over 2. 1 over T average is just 1 over this number. And then log to the base of 10, 1 over T average is just log these numbers. Okay? Are you all okay with that table? Yeah? Okay, good. Make sure that your values are all to 3 significant figures. Okay. Rate can be expressed as this equation. The rate equation is given as this. So log 1 over T average is equals to N log V plus C. This looks like a Y equals to MX plus C equation to me. Y equals to MX plus C. They already said, oh, they don't say. They say C is a constant, okay? Can you see what's your X and Y's on the graph? What's your X? Log V, right? And what's your Y? log 1 over T average. So can you see that? Y, X. Okay, so you should expect it to be a straight line. They also mentioned that V is proportional to concentration. So if the volume increase, concentration also increase. Plot a graph, use the cross, draw a line of best fit. Did you manage to draw your graph? Plot your graph and get a straight line? This time, you will not consider the origin because, well, we're not starting at the origin anyway, okay? So you just start from whatever point you started with, and you try to draw line of best fit. Now, a common misconception is line of best fit does not necessarily need to have all your points sitting on the line, okay? They can, all of them can sit on the line. Some of them can sit on the line, or even none of them can sit on the line, yet still be the line of best fit. As long as the line is in the middle or between all of your points. So not necessarily on all of your points. Okay? Did you manage to get some gradient? What sort of gradient did you get? Because the next one, they want you to find the gradient, yeah, to three significant figures. Did you manage to find your gradient? What is it? Apple, what's your gradient? 0.925. Sorry? 0.95. The others? 0.9. Yeah, because my gradient is wrong. Danish, what's your gradient? 0.9? 0.9 saja. Mine should be 2.5 minus 2.20 divided by 1 minus 0.84. Where did I go wrong? I remember reading one of the 2.05. Okay, sorry. This should be 2.05, not 2.50. 2.05. That means 2.05 minus 2.20 divided by 1 minus 0.84. Yep. So mine is 0.938. Make sure it's to three significant figures. Did anyone get a different answer gradient from mine? Okay, your gradient. So expectedly, we will all get different values for the gradient, okay? Because, well, we may have different lines of best fit. Okay, what's next? What do they want us to look at next? Order of reaction with respect to I minus. Okay, so here we have a concentration rate. This brings us back to the topic reaction kinetics. When you have a rate concentration graph, okay, if it's a straight line, do you remember which order? First order, okay? So for rate concentration graph, if it's a straight line, I don't know if I still have here reaction kinetics. No? That's equilibria. There we go. So I would just like to remind you of the graph that you have looked at before, a few months back. it would be this graph, rate concentration graph. Okay, so if it's a horizontal line, it's zero order. If it's a straight line, it's first order. And if it's a curve, it's second order. Okay, so this is an example where, yes, you are expected to know. What did I? You're expected to know your theory as well. Okay? So this looks like a first order with respect to iodide, sorry. First order with respect to iodide. Okay. Done. Question 2. A student was given a sample of an unknown group 2 chloride. The student dissolved 3.172 of the unknown group 2 chloride in distilled water. So what happens when you dissolve this chloride in distilled water? It just forms, there's no reaction. They just break down into their ions, okay? 2Cl minus, right? And then when you add silver nitrate, same thing, silver nitrate is an ionic, soluble ionic compounds. So it will break down into Ag plus and O3 minus in aqueous solution, okay? Then the oppositely charged ions will form a salt or a compound. So you would expect silver to combine with chloride, and then this metal 2 plus to convert with the nitrate. And it turns out that silver chloride appears as white precipitate. So write down the ionic equation. The answer is already there. You want to produce 1 mole of silver chloride precipitate, hence it's a solid, from what are the ions that make up the AgCl? Ag plus Cl minus. Okay, and you just need 1 mole for each because both of them are charge 1 plus and 1 minus. Okay, to separate the filtrate from the residue, so that means after this reaction, there will be some precipitate. Also, there will be solution. Okay, so that's why filtrate is the liquid, the aqueous part. Residue is the solid part that you want to filter out or to separate from the liquid part. Okay, you can carry out using gravity. Gravity is the normal filtration method where you put a filter paper in a filter funnel and then you just pour it out and you should be able to collect the filtrate and also collect the solid or the residue. The other one is under reduced pressure. Now this is a little bit sneaky because you are expected to know an apparatus which you have not seen used before. I have not even mentioned it to you. It is called the Buchner funnel. Buchner funnel. Have you heard of that funnel before? Okay. This is how a Buchner funnel looks like. It has this shape and there is holes in that. I guess you could see it as a funnel as well. It's just that this time the funnel has some tiny holes on them. There's a hint keyword in the question. It says reduced pressure. Okay? Reduced pressure is vacuum. Vacuum has a lower pressure, right? Compared to the atmospheric pressure. So this filtration is called filtration in vacuum. So what happens? This is the setup. You can't just use this filter funnel without a filter paper. You also need a filter paper still. Why? Because the holes are, even though they're tiny, but they are big, and your residue, your solid, will pass through. So that tiny holes is not acting as a separator. It doesn't separate the residue from the filtrate. What separates residue from the filtrate is a filter paper there. You can't see it. Even here, there's a filter paper there. That's why you don't see the holes, okay? So what happens, this tube is connected to a vacuum. It takes out all the air inside the conical flask. Okay, so what's the logic in doing that? Outside, high pressure, atmospheric pressure. Inside, low pressure, because now vacuum, kan? Okay, physicists. Is there any physicists here? Are you all biologists? Yadi is our physicist, but he's not here. Okay, physics from O level, let's try. There's a difference in pressure. Outside, high. Inside, low. What do you think? Logically. Difference in pressure from your physics, just logically. Apple, what do you think? It will push. So the pressure outside will push whatever contents we have on the Buchner funnel. It will push it, so this will allow the water to filtrate out really fast, rather than just leaving it. Oh, okay, we'll just leave. We'll wait for gravity to just, So that's the normal filtration. Here, due to the change in pressure, the solid and the liquid will be pushed onto the filter paper. The solid will pass through, the liquid will not pass through. That's why it's called a filter paper. And this speeds up the separation technique. Okay? So that's the difference between filtration under reduced pressure, aka in vacuum, and filtration normally using filter paper, and then you have a whatever to collect, beaker maybe to collect the liquid. Okay? Right, so you are then expected to draw this Buchner funnel, which you have not seen until today, okay, in your life. So how do we complete the labeled diagram? Okay, so complete the labeled diagram to suggest how the student could filter the mixture under reduced pressure. Okay, so Buchner funnel is drawn like this. And you must label, there is a filter, no need arrow, sorry. There should be a filter paper, Without a filter paper, the filtration would be useless. I can assure you, solid will pass through. This one is your Buchner funnel. And, okay, something is missing from my drawing. Can anyone see what's wrong? I want to create a vacuum. Air. It's not sealed. Can you see here? It's not sealed. So I have to seal it using a corkscrew just to show that it is airtight. It needs to be airtight. Otherwise, how can I create a vacuum if it's not airtight? Okay. They say it's sealed with a cork around the funnel. And that is how you get 2 marks. State one major advantage. Well, I've already said the only reason why we use this Buchner funnel and this vacuum filtration is because it's faster. The pressure, the high pressure outside atmosphere will push the water or whatever filtrate down, and this dries out, this filters the residue from the filtrate really quickly, rather than just to leave it to filter out. Okay. Next, the student rinsed the residue, transferred it to a crucible, and placed it in a warm oven. What should the student do to ensure that the drying process is complete? How do we know that there's no more water removed from the solid? What can we measure to confirm that? The mass, okay? If you measure the mass of the solid, maybe after 5 minutes of drying in the oven, and then you measure the mass again after 10 minutes of drying. If there's no change in mass, that means the drying process is complete. Okay? If the mass continues to decrease down, that means there's still water. All right? Why can you not say, well, we can touch the solid? Well, we don't know that. Sometimes we touch the solid, but there's still small amounts of water trapped between the solids. Okay? So if we use mass, at least we can say for sure, well, the mass is constant. So warm or heat until the mass of the solid is constant. Okay, the next part, you are asked to find the number of moles of silver chloride. So just make sure you use the N equals to M over MR correctly, but it's for AgCl. So the MR would be for AgCl. Ag is 107.9 plus chlorine 35.5. And you should get 0.04, the answer. 0.04 mole of silver chloride formed. Did you try this calculation? Yep. Okay. Did anyone try the next one? Did you try to do the next question? No? Okay, so let's see. Use your answer to calculate the mass of 1 mole of the group 2 chloride. So the mass of 1 mole is actually the MR. Remember that MR has a formula of grams per mole? So if we make this 1 mole, then MR is just the mass per 1 mole of solid. Okay? So the mass of 1 mole means the MR. The question wants you to find the MR. Okay, then you say, right, MR, fine. You know the moles of AgCl, okay? That means the moles of AgCl is also the moles of Cl minus. Okay? So I will bring your attention here. Whatever the moles of AgCl is, the same number of moles of chloride. Do you agree? Because 1 to 1. Okay. So that means my moles of chloride will also be 0.04 based on the previous answer. However, I'm not interested in the chloride. I'm interested in the metal chloride. What's the relationship between the metal chloride and the chloride? Is 1 mole of metal chloride is equals to 2 moles of chloride. Okay? So how do I find the number of moles of chloride? 1 is to 2. So whatever the number of moles, if I have 0.04 moles of chloride, the number of moles of metal chloride would be half of that number. That's why I found the number of metal chloride to be 0.02. Maybe I should move this first. Okay. Once I am happy with that information, salah. This chloride is also the same for that 2Cl minus. Okay. Once I know the number of moles, so I started with number 1 here, I find the MR because that's what mass of 1 mole is. Okay. MR is equals to mass over mole. Just rearrange. N equals to M over R. N is equals to M over MR. So MR is equals to M over N. So my MR for this metal chloride is 158.6. Now you may be wondering, where or how do I know the mass of magnesium chloride? You go back to the first part, You go back to the first part. This is the mass of MCl2. Okay, going back. Okay, if I know the MR of my metal chloride, how do I find what the metal is? What do I do? I know the MR of this MCl2. How do I find what metal that M is? Yes? How? What can I do with this information? Where do I go next? Minus the mass of, or the AR of chlorine. You all agree? Yes, good. So this 158.6 is when you add up the AR of the metal plus 2 times the AR of chlorine. Okay, so after working that out, I found that M is berapa? What's the AR of M? 87.6? Yep. Okay, good. 87.6. And they already mentioned that the metal M is of group 2. And you will find that the metal that has an AR of 87.6 is siapa? SR? Strontium. And that is how you work out the metal. Okay, last question. State and explain how the number of moles of silver chloride ion form if the student used tap water instead of distilled water. The difference between tap water and distilled water is that distilled water, it doesn't contain any ions. Supposedly, it just contains H2O. Whereas tap water, I'm not sure in Brunei what ions we have in the tap water, but usually they add ions. Okay, fluoride ions being added to supposedly help with fluoride bones, I think, if I'm not mistaken. Chloride ions is usually to kill bacteria. Okay, so there are chloride ions in tap water. Just not sure in the tap water that we have in Brunei what other ions we have, but this is typical tap water. Okay, so the effect this would have is that the chloride ions from the tap water will add on to the chloride ion in the silver chloride solution. So you would have higher how would the number of moles? Okay, so that means if you have more chloride ions, the silver chloride will also increase. Okay, so this will increase the number of moles of silver chloride because tap water contains chloride ions. Okay, And that is the end of our paper 5 discussion. Nina, when you're done copying, can you please stop the recording? Thank you. I'll give you 5 minutes break, and then we will do some questions.